1994, Aaron Weiner published a paper where basically what is the fundamental limit of a wireless system? Well, why don't we just process all antennas together? And so this becomes effectively, in this case, was an uplink. At the time, the focus was an uplink. It becomes a multi-access channel with basically vector observation and derives some interesting. Then, quite a bit later, people start looking at the downlink version. Downlink turns out to be a much more complicated problem, but it becomes a sort of vector Gaussian broadcast channel that somehow I, in slow motion line, started, and then a series of papers, David Shade, Vishwanath, and Goldschmidt, Chinda, and Vishwanath, and then finally Weingart, Steiner, and Shammai closed the problem on the capacity. This was a much more complicated problem, but still, then there is some uplink, downlink duality that somehow relates this vector uplink or multi-access channel downlink. So great, this was a lot of excitement, but the problem is how do we actually process all these antennas together? Well, there is a lot of practical problems, right? And people have tried. In fact, at the time of the 3G and then 4G, the industrial name of this was COM, so it's coordinated multi-point. Not so successful because there were a lot of technical problems. More recently, so-called the centralized RAN or cloud RAN, basically, people found that if you distribute the antennas and then somehow virtualize the base station in some data center, there are some advantages in coverage and processing and flexibility. Still, these systems do not scale. It's like unthinkable to put all the processing in one point and convey thousands of different antennas, convey the signals in a single point. So more recently, people came up with the idea of self-free, user-centric wireless networks. The scenario is, a typical scenario is like super dense environments, like sport arenas or very like marketplace, mall, the train stations. Or also now people are looking at the 6G that is coming. There's a migration between the so-called FR1, which is the frequencies of cellular system today, to FR3, which is the segment of, say, from 7 to 14 gigahertz. When you go up in frequency, propagation becomes harsher, so operators do not want to deploy more cells, or at least cell sites, and therefore there will be a shrinking of the coverage, leaving holes, and then somehow you are almost forced to create a sort of cooperation in order to fill the holes and guarantee coverage. So what is a self-free user-centric wireless network? So basically, the idea is that instead of predefining cells and sectors that are infrastructure-centric, every user should have its own cluster that is like a personalized cluster. All the radio units around it should somehow serve the user. And as the user move around, somehow this cluster migrates. So the user is always at the center of its own personalized cell. In order to do this, in practice, one has to provide a flexible front haul, because we see that the processing is done in these objects that are called decentralized units. And then we have the so-called radio units. And clearly, a cluster is like a logical entity because it's connected to, it has to be set up for a user. And then if when the user moves, some radio units get disenrolled in the cluster, other gets enrolled, and at some point, one has to be able to flexibly route information to the front haul and process this cluster process as so-called software-defined network functions that have to be allocated in the so-called PUs, in the decentralized. So a fundamental concept in this type of network is scalability, which is roughly defined in the following way. Imagine that we have an area A, as a coverage area, and then we have a density of regular units and a density of decentralized units and a density of user equipment. And the idea is that a network is scalable if, as with constant density, as the area of the network extends to the infinity, at no point in the network and no link in the front wall, the traffic or computation load explodes to infinity. So there is no points of concentration. The processing must be necessarily distributed, which, from an information theoretic viewpoint, this poses a lot of problems. For example, this is a problem of multi-access and interference. Inherently is an interference channel. If you cannot process all the signals together, we have interference, or say broadcasted interference. So it's a tough hook. So essentially, given that the information theoretic limits of these general problems are hard, people have focused much more on the algorithmic and say communication theoretic aspects. And you find thousands of papers on self-read networks that have essentially always focused on pilot contamination, pilot optimization, channel estimation, uplink, downlink, recording techniques, essentially with the general assumption that we treat interference as noise, but in a clever way. So using MIMO, using coding, somehow limiting interference, keeping interference under.
Just a quick question. Should I think that this, when you say density, this is essentially, I'm thinking of spatial point, boson point processing.
Yeah, for example. So here in this talk, I want to focus on something that has been so far not so well investigated, which is how we do random access and how we actually set up these user-centric clusters in a very fast way. Because all the analysis and the work that has been done so far has focused more on how we communicate once the network knows exactly the clusters, the users, every user is given a certain pilot, a certain transmission resource, and so the system somehow knows which users are active, which users are sending uplink pilots, estimates the channels from the uplink pilots, using uplink downlink reciprocity to calculate pre-coders in the downlink, and so on. But suppose that we have a situation like this one, where we have, I don't know, 20,000 users in a stadium. Clearly, they're not all simultaneously active all the time. Some users go to sleep, and then they have something to transmit. So they need to be able to access the system. And in this case, well, we have a little problem, right? Because today, the way a user device listens to the channel, finds the beacon signal of a base station, and then waits for a random access slot, sends this packet, which is like a request to access, a request to resources, and the base station grants resources to the user is going to start transmitting this packet. At some point, it goes to sleep again, etc., etc. In a self-read system, who does what? It's not so clear, right? So in particular, in a somehow unrelated motivations, 3GPP, which is the standardization body, the standardized system, has come up with something called two-step RAG, which is essentially a random access scheme for fast access for sporadic communication, so-called machine type or IoT communication, where sporadic users may just somehow very quickly access the random access slot and send some data without waiting for permission. So normally you would do a four-step RAG, so preamble, resource allocation, data acknowledgement. The two-step RAG is preamble, data, acknowledgement. And the way it works is that there is a common code book of, in this case, preambles. So there are SADO2 sequences that have nice properties of correlation and cross-correlation. Every sequence points to a chunk of time frequency, which is the push opportunity. And basically, a user sends a preamble, which is announcing to the base station, I'm going to send data in that particular slot, and then send the slot without asking permission. If there is a preamble collision, well, it will somehow use the same slot, and then things go back. So they typically the acknowledgement doesn't happen, and so the user understands that there's something. Okay, beyond this, how do we look at this problem? Well, somehow inspired by this philosophy, we say, okay, suppose that we have this cell-free system, and now all the every now and then, periodically, for example, all the radio units together send a so-called clear-to-send signal, which announces that what follows is a random access loop. So we want users to have a common code book because it has to be the same, like this the library of
coordination is needed.
Right? And in this slot, they will send code words from this code book. There is some processing. In this processing, we want basically the system should be able to identify which code words are active without even knowing who is transmitting, but those are like tokens, right? Estimate the corresponding uplink channels corresponding to those code words, such that very quickly from these estimates, the system can set up clusters of radio units that can beamform, that has to be beamformed, otherwise in this super dense system, there will be too much interference. Beamform very quickly an acknowledgement. This acknowledgement is basically maybe just acknowledging the data that the user has sent, or if this was a request for, say, resources, would just say, for example, okay, I give you this pilot, this slot, this power, etc., such that the user can follow with their, let's say, allocated traffic for a while. So this sort of sending a virtually infinite number of users, only a finite number at every time is active. They all have the same code book, and the role of the receiver is to identify which code words are active, goes under the name of unsourced random access. It was proposed by Yuri Polyansky in a paper of 2017, where he showed essentially some interesting trends that when the number of users scales with the block, basically, well, he found that he finds something called the per user error probability, and was able to analyze the at least upper and lower bound in the say, low SNR regime, so error probability versus ED over zero. And but it's interesting that this sort of information theoretic framework matches almost perfectly this idea of two-step rush of rigidity. So it's one case where the theory came up with some kind of abstract problem that somehow is a perfect match with what actually is the real system. So this problem has been studied quite a bit within two variants. So some people call it activity detection, some people call it unsourced random access. In the case of a centralized receiver. So first of all, in the case of a Gaussian channel, so no fade. For a centralized receiver with MIMO, so with multiple antennas and fading, this has also been studied. There are interesting results. Basically, the model becomes a Gaussian linear model where you may imagine that we have a code book. The column of this matrix are the code words, and the active messages corresponds to, say, non-zero entries in the diagonal matrix that select which code words are active. And then we have channels, unknown multi-antenna channels are the rows of this matrix H. And only the channels of the active users are actually there, the others are zero. So basically the rows of this matrix are some sort of Bernoulli Gaussian process plus Gaussian models. And the goal here in terms of identifying the code words means finding either, which is equivalent, of course, the which elements, which say columns of this matrix are present in this linear superposition, or take this matrix as a sort of measurement matrix, and now which rows of this matrix are non-zero. And this is a compressed sensing problem. This is a block sparsity compressed sensing problem, and we know everything about it. We can do our favorite L2 norm regularization, AMP, etc. And in fact, this problem has been studied quite a bit. So in particular, we have the so-called compressed sensing regime, where the length of this code was L should be, as we know, larger than the number of non-zeros, or the number of active users, plus times a logarithmic factor. Then they have the identifiability regime. The identifiability regime is where we care about which code word has been transmitted, but we don't really want to estimate this matrix. And it turns out that this is a quadratic regime. So the one can show that the number of active users is upper bounded by L squared instead of L, like L like here. And in fact, we have a paper where we came up with an algorithm called covariance-based algorithm that achieves this regime probably. And the interesting thing is that in the so-called identifiability regime, again, we get the activity, so we get the active code, but we cannot get the channels. So this defeats the purpose of being able to be informed immediately with very low delay. So in this talk, we focus on the compressed sensing regime. So just another note is what is the key difference between activity detection and unsourced random access. In activity detection, a similar problem has been posed, and we have studied before, where every user is given one code, and then you want to know which users are active. So basically, every user has his own personal signature sequence. The problem becomes relatively easy. It can be addressed with the approximate message passing, under the assumption that somehow the statistics of the channels for each user is known. So basically, you have a sort of Bernoulli Gaussian process in the matrix of estimate, and this allows to a tractable form of the approximate message passing using a posterior mean estimate denoising function. The problem with the unsourced random access is that every user uses the same code book. Any code word can be used by any user, and so you don't know where the active users are and where they will transmit this code word. So this makes this sort of Bayesian representation much more complicated, because you have one, say, additional layer of randomness, which is the position of the users, that makes things very, very complicated. So basically, we are going to circumvent this problem in a way. Basically, we are basically cheating a little bit. So just to give an example, so what is the statistics of these channels for a user in a given position? So I call the user position Q. A user in a given position of the coverage area, when it's active, well, its channel will be, in fact, a sectionized Gaussian vector, where we have sections for all the n antennas per base station. So we have these sections, and we have different large-scale fading coefficients, which are basically the path losses that each user has with respect to these radial units. So this vector is in fact conditionally Gaussian given the position of the user, or if you want, given the profile of large scale Philip coefficients that are somehow a function of its position. So again, if we want to average over, so remove this conditioning, and the combined statistic becomes a Gaussian mixture, and it's very complicated. So what we do, we cheat, and we say, okay, we are going to design an algorithm that allows a little bit of mismatch. So we are going to take the whole set of the LFC profiles over all the, say, a grid, sufficiently dense grid position of the users. We see this as source. And then we create a vector quantizer. So we cluster these LSD profiles such that we assign a specific sub codebook to each cluster. And then we use a detector that assumes that all the code word in that cluster have the same, when active, have the same LFC profile, which is essentially the representative of the cluster. Imagine a vector quantizer in the points like for every cluster representative. So this yields a very simple tessellation of the plane when the LFCs are simple radial function of the distance, like classical error, path loss exponents, 1 over b to the other. However, we have also considered much more complicated cases where we take a real 3D map of the environment, we place the radio units around, and then we generate the receive signal power by ray tracing. And then we generate for every pixel in the position, which is 1 meter by 1 meter. In this case, we generate a LFC profile, and then we do basically k-means plus Lloyd max to somehow generate a good vector quantizer, and then you see this type of strange regions, which are not so bad. They have some kind of consistency. And this would be the case, for example, in this precise topology, when we have 9 radio units. This is for 9 or 18 clusters. So we will accept this sort of mismatch. And now what we are going to do, now we are going to model the received signal as in the following way. For every cluster, so we use U to index the clusters. For every cluster, we have a sub codebook, and this X contains on the rows the channels that may be 0 if the corresponding code word is not transmitted, or non-zero with the statistics of that cluster, so with that Gaussian, with that specific profile. And at the end, the receiver that takes all the observation of all the radio units together sees the sum of these products plus noise. And our goal is an algorithm that finds the non-zero rows of the matrix X, because the non-zero rows of the matrix X are the channels of the users that are active in each state cluster. So we assume, for analysis sake, we assume that the code book, so the S matrices, are Gaussian simple and symmetric IID with, so they are essentially random matrices. And this makes, of course, the analysis of the corresponding algorithm easy. It can be extended to sub-Gaussian IID, and we have a version that was actually presented at ISAT in June that also consider semi-unitary. So it's a op-amp version of so it's a bit more involved to improve all the stuff, but it has a slightly better performances, but for depending on the dimension, they are almost equivalent. So we will do all the analysis holds for the parameter L going to infinity, so for large L, and the number of, so these are the aspect ratio matrices. So basically NU is these dimensions, so the number of code words in every subcode, and L is this dimension. So this ratio is the aspect, this ratio is the aspect ratio of this kind of matrix. So basically, this is the picture. We have the superposition of the sum of this product S1 times S1, X2 times X2, and the X's are these sort of sectionized matrices with different variances, or the rows are zeros. And so our problem is find the non-zero rows of this. And how do we do this? Well, we do it with this, we call it multi-source AMP, because basically we have a superposition of different sources with different statistics. So the algorithm is very similar to AMP, effectively. The only thing is that we create these residual matrices for each different source, and then we put them together, we subtract, and then we create this. And then we pass this sort of soft observation through the famous non-linearity or say denoising function. And this denoising function acts on the row matrices, and we have okay, so the denoising function acts on the rows. The Q is the expectation of this Jacobian matrix. So this is its Onsager term that is added here, and this actually has a fundamental role in decoupling the iterations and making the analysis asymptotically correct. And we have the following results. So we can define these the construction of a Gaussian process by constructing the two-time covariances for every T and S along the iteration. And this is a recursive construction where basically these guys have the statistics of the rows of the matrix XU, and this is the Gaussian process that we construct. And in this way, implicitly, by basically one by one, we can construct the sequence of these covariance matrices. And once you have the sequences, you can keep going and you can construct the whole joint statistic of this Gaussian process. And the main result is that the matrices are U of T produced by the algorithm at every iteration T have the statistics, the asymptotic statistics, where this sign means convergence in probability of the true matrix that we want to estimate, plus a Gaussian matrix, which is mutually independent from the matrix we want to estimate. And this Gaussian matrix has precisely is IID by rows, and every row has the statistics generated by the state. So basically, this means that this strange algorithm is going to produce for large dimensions along the iterations in the R step. So here, at this point, so before the nonlinearity, it's going to produce something that can be interpreted as the matrix we want to estimate plus noise. And this noise depends only on the parameter of the system. So at least the statistics of this noise depend on the parameter of the system. So this actually is used to design the nonlinearity, because at this point, we have the so-called decoupling principle. So every row can be, every nth row can be interpreted in this way. And now we have an idea of how to design the nonlinearity, because from this Gaussian observation, now we can design the nonlinearity as the posterior mean estimator based on these asymptotic statistics. It would be very difficult to design the real posterior mean estimator. It would be a terrible multidimensional problem, right? But based on at the point where the asymptotics kick in, we can use the analysis that holds for any Lipschitz with some kind of quite general regularity condition nonlinearity. Of course, if you use a bad nonlinearity, you will have a lot of noise. So this term will be giant, and the algorithm may not work at all. But as long as the nonlinearity is Lipschitz, this is true, and therefore we can pick our nonlinearity based on this and use the posterior mean estimator in order to have, this denoising to be effective in the minimum mean square error sense. And it turns out that with this choice, we can also find this functioning kind of appealing closed form, which is given in this way. And also its Jacobian matrix is given in closed form. So this makes the algorithm very tractable and very simple. So that's good. At this point,
Why do you need the Unsourced conversion?
well, we don't need it. It's a little bit of a additional result that we can prove, right? We're always happy when you have it. Actually, we need this only in one result. At some point, I didn't get into the detail here, but at some point we use this analysis also to characterize the false alarm and the say misdetection probability applied after the algorithm. So I'm getting there in a moment. And there we actually need this almost sure convergence. So to prove not that this probability holds only on average, like when expected on everything, but hold like one-wise, you have like an empirical sum of that converges to the example probability. We need that at some point.
For the denoising, you are using MSC?
Yeah, the nonlinear MSC. It is nonlinear because the process, so this X is under this condition is Bernoulli Gaussian. And so that's why we have this basically this denoising function that when you see it like this is it's highly nonlinear because basically the this lambda map is this function and this part is linear. So basically you have like a linear part, but then you have a sort of non-linear weighting factor here because this takes into account. So this depends on the probability of being zero, non-zero, and so on. So it's the Bernoulli Gaussian statistic. And okay, so now that we know how to characterize the up of the algorithm at every iteration, we can say, okay, suppose that we fix capital T iterations. At the end, we have our observation will be in this form, and we know the statistics of this, right? It's like observing what you want to estimate plus Gaussian noise. So how do we do message detection? Well, it becomes a binary hypothesis statistic row by row, where the two hypotheses are only noise or signal plus noise. And the signal is the channel vector, which is Gaussian. So basically, we are comparing two Gaussian hypotheses. One is only the noise covariance. Of course, it's not the channel noise, it's this noise at the output of the algorithm. So the C is what the state evolution predicts at the end, right? When these two are Gaussian independent, then the covariance is the sum of the two. This is the covariance of the channel, which is known under our clusterized assumptions, and this C again. So basically, this becomes and we use a Neyman Pearson test here because we want to balance between false alarm and misdetection probability. We could implicitly, if you know the probability of activity, then you could also use a maximum a posteriori to minimize. But this minimizes an average probability of error. But here the two events of false alarm and misdetection play very different roles from a system viewpoint. So you may want to balance them. So we apply Neyman Pearson, and the good thing is that this Neyman Pearson with the two different Gaussians is fully tractable because the decision matrix is a famous Hermitian quadratic form of Gaussian circular symmetric random variables, and you compare this quadratic form with a threshold, and we know how to calculate the characteristic function of this Hermitian quadratic form. We know how to do Laplace inversion, at least numerically. So essentially, you get it in closed form or through, say, a quadrature rule. That this was one of my first papers, as you can see from the page. At the time, we were interested in coded modulation with fading, and so we came up with this idea of using Gaussian quadrature rules to evaluate this probability of errors. And it turns out that in this case, it was perfect to use this. Okay, so another advantage is that, again, thanks to this characterization, we also can write down the mean square estimation error of the channels. So basically, you can say, okay, let's condition on the transmission to the users that are active and are detected as active. Why we condition that? Because these are the only interesting cases. Because the users that are active but they are misdetected, so there is no acknowledgement. The users are not seen. The false alarms cost transmit power, so they generate the system thinks that there is somebody, but in fact, this somebody doesn't exist. So in this analysis, we take into account this additional interference power, but we don't really care about the rate or the decoding error for this acknowledgement because these do not exist. Right? So the only one that really matter are those that are active and are detected as active. And for those, we can use the so-called use and forget bound, with is a sort of achievable rate, lower bound on the probability of decoding error when the channels are not perfectly known, which is well known in the massive minor literature. And it turns out that, again, I will not explain all these formulas, but somehow these formulas can be evaluated semi-analytically in the sense that we have to calculate this coefficient by Monte Carlo. But because we know the statistics, this can be done offline. So you can calculate offline and plug this in this formula, and you have okay, so we can use this like in a super simple toy model. It's called like Wiener model with two transmitters, so two base stations, where we have only say a group of users with a certain coefficient, and then you create interference with other coefficients, and so we can check the validity of the analysis. So these are every dot curve is an empirical, finite dimensional evolution of along the iterations of the estimate of the channel estimation error, and the thick line is the what is predicted by the state evolution, and you can see that it's not only on average that we have this, but we have really a concentration of all the trajectory concentrate around what is predicted by the theory. And then for this toy model, we compare the case where we run this algorithm centralized, so taking the observation of the two base stations, or decentralized, which we do it for one, we do it for the other, and then somehow we pull the decisions together. And not surprisingly, I would say, we see that for the centralized algorithm, when we increase the crossover interference from 0.1 to 0.9, the performance improves. So we go from here to here. For the decentralized, the performance degrades. Go from here to here. And why? Of course, this decentralized does not interference is interference, so it's harmful. For the centralized, interference is more signal because you process it jointly, so you get more signal and therefore performances. Okay, that's not very. I mean, it's just in a certain sense a sanity check. Things work as they should. Then we looked at a larger system. So we have 2,048 codeword per location for a total of, I think, 16 locations, 12 base stations. And we take the classical at loss function that depends on distance with a certain exponent. And we assume that the decoder assumes that the users are all centered in these red dots, but in fact the users are uniformly distributed, so there is this mismatch. The length of the preamble, so the length of the code is 1024, so we have 2,048 times 16 overall code book of length 1024. So clearly non-orthogonal codes, right? Because the vertical length is much less than the horizontal, right? And nevertheless, we obtain for the case false alarm equal to misdetection, so we can operate at this point where false alarm and misdetection are more or less both at the order of 10 to the -2, which is pretty good. We compare the channel estimates obtained by this scheme with a geniated MMSE estimator that in this case would be optimal, because if you condition on the active users as no, then of course the problem becomes, say, the S matrix becomes, take only the active columns, becomes tall, and this basically you have a linear Gaussian problem where linear MMSE is optimal that can be also analyzed. And so the geniated, assuming the perfect knowledge of the user code words, is the red curve, the AMP theory and the AMP empirical are the blue curves, and you can see that the channel estimation is nearly ideal, in the sense that it's nearly geniated. And these are histograms of the so-called ergodic rate of the downlink acknowledgement, the arcing down. So basically, based on these estimates, we form the user-centric cluster that will simply do maximal ratio transmission and send acknowledgements, which so this tells you how this lower bound to the achievable rate is distributed over the user population. Do I have 5 more minutes?
Sure.
Oh, okay. So I want just to say one more thing, that from these algorithms, we can also extract something more. Effectively, these rows have the statistics of the true channel plus this additive noise, but the true channel without the assumption that all the users are co-located into these cluster centers depends on the user position. So if we can also run a maximum a posteriori probability based on the output statistic of the AMP on the user position by basically quantizing the positions in the grid and then simply writing the maximum posteriori probability decision based on these statistics. And it turns out that so this is basically a way of doing localization of the users. only based on, let's say, received signal strength, because effectively these variances collect the patterns. So there is no problem in straight synchronization, time difference of arrival, array, angle of arrival, triangulation. It is much more, it's much coarser, of course, but also much more robust. So we tried, and it turns out that the performance are pretty good. So in the case of the regular triangular clusters with the radial path loss that is just a radial function, of course, it's the best case. We see that our scheme, which is for some reason is location based because the code is partition to location. This is the histogram of the localization absolute error in kilometers, and this is the oracle that basically is simply the quantization on the closest point in the grid. And we see that this error essentially is dominated by the quantization of the grid. Is essentially is on the oracle. By comparison, this would be the performance when we don't do this partition of the code book. And so we have every user can use any code book anywhere. And of course, this works much worse. So then we tried with something more realistic, which is this kind of things. And here things are not so good, of course, because the path loss is not a radial function. Who knows what it is? It comes from the ray tracing. But we have this type of example. So for example, this is one cluster, which is not even a convex. They are not convex sets. They are not compact. So for example, using centroid approaches will give you points that are even outside the cluster. But this maxima posteriori is somehow able to the blue points are the true positions. The yellow points are the estimates. It's not so bad. And so, for example, this is the case, again, histogram of error. This is in meter now because the sizes are smaller. And we see that essentially we can, maybe up to 80%, we can get an estimation error in the position in say, in the order of 10 meters, which for a local area network is already pretty good. Not super good, of course, but good enough, for example, to allocate radio units and create these user-centered clusters very, very quickly. So that's another little byproduct. Now what we are, the work in progress, okay, so this is just a summary, but the work in progress is we are basically looking at the real case. The real case is a bit more complicated than that, because the wireless channel is not just a single coefficient, it's an impulse response because we transmit wideband. So, and then the problem is what to do, right? You can basically ignore the fact that there is a delay spread, multipath, but it's not, then this model is not really correct because you have delays, you have propagation delays. So these arrive misaligned with intersymbol interference. So we look both in the time domain, exploiting properties of the other two sequences, and basically cyclic correlation and cyclic cross correlation of the sequences. Another approach is to go to the frequency domain and therefore have essentially a sort of basically work on different subcarriers, like in combo frequencies. And so you see this delay misalignment as phase factors in the frequency domain. The good thing that we are trying to do is that when we go wideband, then we have some form of also delay estimation that comes automatically as another byproduct. And then we hope, but it's not yet sure how to do it. We hope to do some sort of clever data fusion such that for the positioning, instead of using just the path loss, we can also use time difference of arrival. And when we have time difference of arrival, this identifies some sort of elliptic regions on the plane. And this can be maybe through some machine learning, for example, fused together in order to improve the localization. And so that's essentially what we're talking here. And so this concludes my talk.
Any questions?
Why is the MSc for denoising?
Right. That's a good question. So I think it comes almost naturally when you have this sort of formulation, which is Bayesian, because we have the a priori of this matrix X. Because basically the state evolution represents or predicts along the iterations the covariances of this virtual adequate noise. So the fact that you can interpret this precise step before the denoiser as what you want to estimate plus Gaussian noise. And therefore, the minimum mean square error estimator as denoiser is somehow targeted to decrease as much as possible the variance of this algorithm, right? Because imagine you are observing something that has, in this case, it's Bernoulli Gaussian, it could be a different distribution, maybe it's discrete, plus Gaussian noise, and you want to pass to the next iteration something that has less noise, right? So the nonlinear and nonlinear minimum mean square error is the way, right? Because of the MMC decomposition, you can always write basically what you want to estimate as your MMC, your conditional mean plus innovation. And this plus innovation, if you control the variance of this innovation, which is uncorrelated, at least in the second order, right? If you go to second order, this is the right thing to do. There may be higher order considerations, but if you go to second order, this is the way, you know, to minimize the noise at the next step. So it's kind of like natural in this context. Yeah.
Oh, thank you for your presentation. And I wonder what's the status of unsourced multiple access in academia and industry, like, because it's been a few years since IT society started working into it, and I wonder for like, is it mostly done in the IT society and the comp society just get started?
Okay, good question. So let's start from what is the status in industry. Industry, it took me a long time, and I can tell you a lot of meetings is almost frustrating to convince some people from industry with whom I'm collaborating that this unsourced random access actually matches what is prescribed in this 3GPP two-step batch thing. So they just don't see it. They say, "Oh no, this is theoretical," and but we do this. No, look at conceptually is a one-to-one mapping. Conceptually, of course, sequences are different. The detection they specify something that's much simpler. Simply to mention filtering and all it works. But conceptually is the same thing. So that's the right model, right? If you want to improve that, that's the right tool. From a, let's say, academic research viewpoint, I think that there is still quite a bit to do in terms of the fundamental limits. So the Gaussian additive case, where everybody has a known coefficient, so they're all equal to 1, right? Is no, because it's the first thing that Poliansky characterized. Then other people, including myself and co-authors, have limits of on achievability and converses for the MIMO case. The MIMO case where there's an IID channel matrix and which is that no, it's fixed over the block, It's like sort of block fading, but it's like in this case, where the channels are fixed over the block, but they are unknown. Non-algorithmic using bounds. So from a fundamental limit case, for example, I'm not aware of this kind of achievability encompasses for when these matrices are more complicated, not just Gaussian AID, but for example, here, these matrices are structured with these variance profiles. I'm not sure that there exist achievability encompasses for this case. And of course, the algorithmic side is still quite under research, right? So this is one method. There are several others, and so I think it's still like an ongoing topic. And I think, and this is what we are working now at this point, based on this sort of partial successes, we are looking at problems of this kind, where we use what is called a sparse superposition LTC codes. So basically, the codes have this structure. There is a random matrix, and then there is a non-binary LTC. And then basically the non-binary symbols are encoded into so-called one-hot symbol. So vectors of all zeros and a single one. And these select the columns of this matrix. So this part alone is the so-called sparse superposition codes invented by Baron and Joseph, and which probably achieve capacity under maximum likelihood and also under coding, but then people found a way of concatenating LTCs in this way. And then there is a nice recent paper by the group of Krishna and Narayanan where they analyze an plus belief propagation coder for these codes for the Gaussian case. And now here we have the case where we have done the blind let's say one input M output. So these we have, imagine this is the code word, this is the spark code word, and this is a row of unknown antenna coefficients. So you can write these in the following way. You have the spark matrix, and then you want to find this is the vector of the ones times this. So this is a rank one matrix where you have an unknown vector which is repeated around in the correspondence of the ones, and it turns out that we have an algorithm that can be again analyzed, for which the theory works, for which basically what we see is that, so this is the block fading, it's like the sign of block fading. This is the information access probability with perfect chance and information to the receiver. This is pilot base when you try to estimate the channel and then you decode. Sorry, no, this is the 3GP pilot base case, short block case, and this is what we can do. So basically, this would be like a completely blind receiver that does decoding and channel estimation in one shot by iterating these things. It has two, I would say, advantages, potential advantages. One, you don't need pilots. So this is a single user case, but now we are extending this to the multi-user case. And now the dimension of the uplink pilot, because every user has to send an orthogonal pilot, otherwise we have contamination, depends on the number of users. So hopefully we can do better than sending orthogonal pilots. So we can spare in the finite regime, a non-asymptotic regime, we can do better than explicit piloting. The second thing is that even for the single user case, at the end of the decoding process, when you are on the good side of the convergence, it's like using the whole code word as a giant pipe, because eventually you know the code word. So one problem that wireless people have, industry tells me, is that the uplink channel estimation is very unreliable because the users transmit a low power. So you transmit a few pilot symbols. It's maybe good for the receiver, but it's not good enough to use for using reciprocity to compute good quality pre-coders in the down. But here you're transmitting the whole code. You use the whole code as a giant pilot. So basically, the power, even if it's the power is small, but you are integrating over a long interval. And so hopefully the channel estimation quality at the end of the scheme is better than sending just the pilots and then just use the channel estimate from the pilot. And so we hope that this may actually improve also the downlink because you get a better pilot estimation. But again, this is really, I mean, this thing, actually, this paper, I got the preprint from my students 2 days ago. So it's really work in progress. And we have only the single user case. But the proof work and the analysis work, so it's kind of. So I think that there is still some, not so new, but there is.
The algorithm, you have some over you. I think it's, I'm not sure who's doing the sum, but the base station, does every user have to do its own sum over their local?
No. Yeah, okay. You're right. Let me explain again. So, imagine, okay, let's get the signal model. Okay, here or here, right?
Yes.
So, we have all these locations that are this view. In every location, some user pick some code words, they all transmit, and then collectively all the radio units receive. So what you get at the radio unit is the superposition, just because the channel, the transmission happens at the same time at the same time.
Right, sure.
So the sum is done over here.
That's the physics, but then in the algorithm, there's a summation. I want to know who's doing that summation.
The algorithm is completely centralized. So these are the
This is
algorithm.
the centralized.
Yes,
Oh,
the
that's
algorithm
what
is run. The algorithm collects all the data, also all the RACH slot received from all the radio units, and does the centralized.
So this doesn't yet have that density scaling that you
No,
want. Okay,
Exactly.
okay.
You got me there. That is not
Not
scalable.
there yet. Okay.
That is not there yet. Sort of message passing consensus version of the distributed version of this is to be seen. I think it can be done because at the end the only point where we concentrate is this one.
Right,
Right?
exactly.
So
Yeah,
it may be that there is a way to somehow spread this information and do some sort of consensus distributed. That is will be actually very interesting aspect.
I don't think we have anyone, I mean, there was, Al Hero was on Zoom, he's out. Any other questions? If not, let's thank Giuseppe.
Okay.
He'll be here tomorrow and then he'll probably be there, I mean, he may be able to visit a few weeks from now.
Yes.